next topic, and these are some more recent development, is the notion of eco-materials. So these are a class of materials. They are called eco-materials because first, their extraction and processing poses very little environmental impact. They are very abundant in nature, and thirdly, there are very few laws or restrictions on usage. So if it satisfies this, it's called an eco-material. So whenever possible, we try to choose an eco-material. So what are some properties of eco-materials in a little more detail? Firstly, you must have an abundant source of this material. Recycled supply should be, you should be able to utilize a recycled supply. Sometimes we cannot recycle certain things. Third is that the material requires low energy consumption in terms of extraction, purification, and processing. The material has little or no environmental impact, whether it's acidification or global warming potential, has little or no legal restrictions on its use, and the material can be used over an extended period of time. That's a good thing, right? Because if it has a short lifespan, then we have to replace it. The more frequently you replace stuff, the more they impact the environment and cost. And the material can be either renewed or recycled. So these are some properties of eco-material. So the criteria or guideline here is, if you have a choice of eco-materials for whatever application you're dealing with, choose from that list. Another topic that is quite contemporary is called dematerialization. So regardless of how well a product is working or how well a material that has been used as choice is doing, we can always improve the design by reducing the amount of material. But you cannot do it this blindly. You have to do this by a careful design using stress analysis. In other words, if I find an engine cylinder for an automobile to be very heavy, and I conclude, okay, cast iron is not a good choice, I'm going to replace this with copper, which may be less dense. Well, that's not a smart way to proceed, because copper can yield a cylinder that's lighter, but does it have the thermal properties? And there is an explosion inside the cylinder in the internal combustion engine. Can it handle it? So these are other things. So it's not just reducing the amount of material per se. It is making sure through a stress analysis that the reduction in material will not leave the product compromised. It's still as safe and as functional as before. So we have, for example, an engineering analysis method called finite element analysis. This is a computer software that will allow you to virtually apply loads within a CAD software and simulate what happens. So you can find out which areas are highly stressed, which aren't stressed, and parts of low stress, you could reduce the amount of materials. Portions that have high stress, you should not be reducing the amount of material. Some rules for dematerialization is you avoid sharp corners so that you can have thinner walls. So what does this mean? So here in the upper left-hand corner, we are looking at a product that's got sharp corners. Right there and there, you got sharp corners. Any place where you have a sharp corner in an engineered product, the stress is usually locally very high. And because of that, we try to make it thick so it doesn't break. Now, if you don't have sharp corners, but you have a rounded corner like so, the stress is lower, and we can get away with thinner wall. You can compare this and this. The walls here are thinner. So dematerialization, but I'm not compromise the product. Another rule is use a greater number of supporting ribs, smaller supporting ribs rather than few large ribs. How does that look like? Well, here's the portion of the design that shows you two square-shaped ribs. They are pretty thick and use a lot of materials. What I can do is, instead of having that, I can use a rib that's half as thick, have more of them, but overall the amount of material used will be less. Another rule is when sheets of metal or plastic are used, you can achieve strength by supporting using bosses and ribs. I'll show you what a boss looks like. Instead of using a thicker sheet, because you're increasing material overall, if you use a boss, it's localized. Now here is an example of a plastic sheet, and this is a boss, and that's how the front view or cross-sectional view looks like. It's a hollow, but it's like a little cylinder. It gives it some rigidity. Now I could just increase the thickness over here overall, but that would increase the amount of material. I could place strategically a few bosses around the flat surface and improve the strength while decreasing the material. And the last thing is gussets can aid in designing thin-walled housing. So what does that look like? You're looking at this diagram here. You're looking at this L-shaped part. If the the two legs of the L are too thin, then it could fold over, right? So in order to avoid that, a lot of people will make the two legs really thick so it doesn't fold over easily. Now instead of doing that, you can have a thin legs, but you can use these things here, the triangular. It looks like it's a little bracing. These are called gussets, and they help you reduce the amount of material in a design. So again, dematerialization, obviously the word de and then materialization means taking out material or using less material. It's not simply that. You can use dematerialization as a strategy only if you're not diminishing the strength of the product. To conclude, these are some very general purpose advice as far as the chapter goes in terms of material selection. When you have to use materials, try to get most of your needed materials through a recycling stream rather than extracting materials afresh each time. Choose abundant, non-toxic, non-regulated materials for obvious reasons. Design for minimum use of materials in products, processes, and in service. So if you use less material, then there is less energy impact, less environmental impact. And design for longevity, refurbishment, and recycling. Longevity means if your car can last 30 years, then as opposed to lasting just 10 years, if it is just 10 years, you'll need to buy 3 cars in a 30-year period. Here you can make, many people you may see driving the Chevy pickup truck, which probably has 500,000 miles on it, still going, right? So that's wonderful because that's less impact to the environment as opposed to buying every decade a new product. If you can refurbish it, sometimes when your Chevy truck gets quite old, you can rebuild the engine or do something. Does the product allow for that? And finally, when it's all done, can we recycle the body panel of the Chevy truck and the engine and the other parts, the transmission, etc., be recycled? So we need to keep these 4 broad-based strategies in mind as we go about selecting materials for products and processes while making sure that they do very well from an environmental standpoint. Thank you.